Imagine a flock of birds weaving seamlessly through the sky or a school of fish swimming in perfect harmony. These mesmerizing movements, long studied by scientists, are now being recreated in simulation and by robots-in-the-loop approach only using visual information. These kinds of movements are referred as collective motion. And collective motion has traditionally been implemented, disregarding the limited sensing capabilities of an individual. Instead, most models rely on the knowledge of interdistance between neighbors, something not available for animals. But now there is a model that do not rely on artificial metrics but instead uses early vision, as animals do, to enforce a set of 4 rules that are followed independently by everyone in the group. This model assumes that everyone sees every other as spheres. Therefore, individuals are not individually recognized. They are represented by their shadow at their corresponding optical position. This is a binary representation of the field of view. The first rule, attraction, represents the group's inherent desire to stay together. Without attraction, individuals would naturally move away from each other. It is implemented by considering the optical size of each shadow. The second rule, alignment, reflects the group's tendency to move in the same direction. Without alignment, the individuals in the group would have difficulty keeping up with each other. It is achieved by measuring a visual parameter known as optic flow, which describes how we perceive movement relative to our own viewpoint. The third rule, avoidance, was introduced in this study, and it reflects the individual tendency to avoid others in their vicinity. It is implemented by changing the attraction based on a threshold on the optical size of each shadow. The last rule, an anchor, was introduced in this study, and it reflects the group's confinement on a set location. It works similarly to the attraction rule but on a virtually set key location. For the robotic implementation, we had a delay that is equivalent to an individual reacting to a past position or an old state of the world. This was incorporated in the simulation as a time delay between the measurement of the visual field and the result of the algorithm. This study implements the visual collective motion model in a robot-in-the-loop approach to reproduce these behaviors with a flock composed of 10 independent spherical robots. Another milestone achieved with this model is bridging the gap between simulation and physical experiments by demonstrating nearly identical behaviors in both environments with the same visual model. To conclude, we show that our minimal visual collective motion model is sufficient to recreate most collective behaviors on a robot-in-the-loop system that be implemented using several individuals, behaves as numerical simulations predict, and is easily comparable to traditional models. This work pushes forward biologically inspired robotics, with potential applications in swarm robotics, search and rescue missions, and automated monitoring systems.